Now that we are familiar with set builder notation, let's look at rational numbers. So if I had to express a set of rational numbers, I would have to say they are a set of elements of form P by Q such that P and Q, they are integers. The number Q, which is the denominator, can't be a zero. So if I was given a number of the form a by 0, this does not make sense. I can't divide by 0, so we can't have any such numbers. So we'll require that the denominator q is not 0. Furthermore, we also require that p and q have no common factors. For example, I could write the number 2 by 3 as the number 4 as 4 by 6, and I could write this as 8 by 12. I could write this in many different ways, but they're all the same number, right? So I don't want repetitions of the same thing. To ensure that I don't have repetitions of the same thing, I'm going to use the least form, or the simplest form. So to do so, we require that they have no common factors. So 2 and 3, they're prime numbers. They don't have any common factors. So yeah, that's a form that we could choose. Although it's not necessary that they must be prime. I mean, another example could be, let's say, the number 10 and the number 9. Yes. So 10 and 9 don't have common factors, but they're not prime. Yeah. So these are examples of elements that we will see in the set of rational numbers. But simply put, I am able to write any rational number as a fraction of two integers. It's an integer divided by some other integer. It's an integer divided by some other integer. That's the main gist that we need to hold on to for now. So if I told you that, well, how may we compare the set of rationals with the set of natural numbers? Which of the two is larger? Okay, so we can actually, once again, form a bijection. How? So let us consider sets of this form. It looks a bit complicated, but I'll break it down slowly. So let's say I have a set AI, where I is a subscript. I can pick different numbers in the place of I, and I'll show you how it makes sense. So we have elements of the form P divided by Q, such that this ratio, right? It's a rational number, as in the denominator and the numerator are integers. But furthermore, it's a ratio such that their sum is the number I. So I have this subscript I over here to denote that the sum of these two numbers, P and Q, must be equal to I. That's the kind of sets I want to deal with. So in this case, what are the rational numbers we can write within this restriction? So consider this the set A1. If I just have one to pick, that means the sum of P and Q has to be 1. If the sum of P and Q has to be 1, and we know that Q can't be 0, right? So the only choice is that I pick Q to be 1 and P to be 0. So this number is basically 0. If I can't divide anything, I can't divide anything with 0, but I can divide 0 with anything else, and the result is 0, because I can't, well, there's nothing to divide. It's just nothing. So this number is 0. If I had A2, then I could pick 1 in the numerator, 1 in the denominator to form the number 1. And then I could just have a -1 multiplied with it and have 1 in the numerator, 1 in the denominator, and write the number -1. So this is the only valid combination that we can make, because if you told me to write 0 by 2, the problem is this number is precisely 0. And I already have that in a previous set. So I'm going to exclude that. If I have something already present in a previous set, I will exclude it. And if you told me to write the number 2 by 0, because why not? I once again face the same old issue that this number doesn't make sense. I can't have 0 in the denominator, right? So the only valid combination is the number 1 and -1 written in this way. So next, if you told me to show you what the set A3 looks like, I could choose 1 in the numerator, 2 in the denominator to form the number half. I could have 1 in the numerator, 2 in the denominator to write the number -half. Similarly, I could write the number 2, and -2. And once again, these are the only valid combinations because the number 0 by 3 is already present. This number is just 0, and that's present in A1. And I can't write 3 by 0. I already explained why. So now finally, does it look the same forever? Is it just numbers of this pattern? Not really. If I go further along in this sequence of different sets that I can have, like let's say I looked at A29, what would it look like? I'm not going to list everything. That's not possible. But here are a few examples. I could write the number 22 by 7 because the sum of these two numbers is 29. That's a rational number that will be present in this set. I could write the number 7 by 22 because the sum of these two integers is 29. I could write the number 20 by 9. I think you get the idea. I can write any number of this form. And I can, so basically these are the numbers I would have in A29, and this goes on forever. Now, as in the set A29 doesn't go on forever. This is a finite set. What goes on forever is the AIs, because I'm free to choose I from every set of from the set of every natural number. Yeah, so in this manner, uh, I would have an infinite number of sets, but each set itself is finite. Now, why do I need these things? I need these things to show you that there is a bijection. And how do we form this bijection? We just list out the sets. A1, A2, A3, A4 in sequence. We list them out one by one. And we observe that the first set, A1, just has one element. So I count that element with A1. The second set, A2, has two elements. I use 2 and 3 to count its elements. I use 4, 5, 6, and 7. 4 numbers to count the 4 elements of A3. Then I again need 4 elements to count the 4 numbers of A4. And this goes on. I can keep counting in this manner forever. So you might ask, well, if I count in this manner, what if I miss a number? Well, we won't really be missing any numbers. And why so? Well, for starters, given a rational number p by q, it will be present in the set A p plus q. And how do I know that? Like for an example, consider the number 22 by 7. The sum of 22 and 7 is 29. So this number is present in the set A 29. So somewhere further along these lines, right? So I just keep going, and then somewhere there is an A29. I have its elements listed out, and I will have natural numbers that go along this line mapped to it. And the mapping is producing unique pairs. None of these pairs will match because since I've sequentially listed out each and every natural number, the natural numbers have been listed sequentially. So the first element can't match. I change the pair, the first element changes. And in similar fashion, because I have generated these sets such that if an element is already present in one of the previous sets, I won't include it in the sets that come later on. For example, I'm always excluding 0 because that's already present in previous sets. I will continue to do this in the same fashion. If an element is already present in one of the previous sets, I will exclude it from the sets that come later on, right? So by doing this, I'm ensuring that nothing gets counted twice. Everything gets counted and gets counted exactly once. So this is a bijection, and as I have explained previously, it behaves as if I have precisely counted every single rational number using natural numbers.